significant figures. Significant figures, which I usually abbreviate as sigfigs. Significant figures or sigfigs basically help with writing numbers to reflect their precision. So essentially they tell you how precise any measurement is. How precise any measurement is. Now before we continue, we need to understand what does precise mean. So when you make any kind of measurement, we can describe the quality of that measurement by using two parameters, and those parameters are accuracy and precision. There's a difference between the two. Accuracy means how reliable is the measurement that was made. What that means is usually when a measurement is made, for example, if I want to measure length of let's say my computer screen, and my actual length, that the true length that the company tells me is, let's say, 16.3 inches, but when I measure it, it comes out to 15.4 inches. So this is the true measurement, and this is the actual measurement that I made. Okay, this is, let's not call it actual, let's call it the measured value, something that I measured using my ruler. So how different is my value from the true value? That is called the accuracy. So if it is close, then it is an accurate measurement, but if I measured the value to be different from the true value or the actual value, that means my measurement is not accurate. So accuracy refers to how close the measured value is to the actual value, or you can say the true value. Okay, precision on the other hand refers to how close a series of measurements are to one another, which means how reproducible are my measurements. For example, again, I want to measure my screen. This is the true value, but I made a measurement 3 times, because usually in any experiment, if you're making a measurement, we scientifically want to make at least minimum 3 measurements. So I make first measurement 15.4, I make next 15.3 inches, and I made the third measurement, which was 15.0 inches. So if you look at these 3 values, they are pretty close to each other, which means I am very precise in my measurements. It's just that it is not very accurate. So how close are your own trials? These measurements are called as 3 different trials. So how close are your own measurements to your own other measurements? That is called as precision. It refers to how close a series of measurements are to one another. Let's take an example here as shown in the picture. This is the true mass, the blue line that represents the true mass of an object, which student A, B, and C have made measurements, and these are their measurements. The first one is 10.4. The second measurement, these are your trials, right? The second trial is 9.7, 9.9, 10.3. So these are the 4 measurements made by student A. None of these measurements are actually same as, their average comes out to 10.13, which is not same as 10. The true measurement is 10. So it is not a very accurate measurement because it is not 10. And all these 4 measurements are very different from each other. So they're not close to each other. Forget the 10, forget the true mass, but they're not close to each other itself. So that's why this measurement is also not precise, or it's imprecise. Student B got these measurements, 9.7, 9.8, 9.7, 9.8. The average comes out to 9.79. It is far from 10, which means it is also not accurate, so it's inaccurate. But all the 4 measurements made by B, student B, are close to each other. So that is why the person's measurements are precise, which means they are doing the right thing. They are measuring 4 measurements how it should be measured. So they are measuring, it's precise, but it's just not accurate, which means they either are not reading their measuring device correctly, or something's wrong. They are doing something wrong here with the measuring device. Either the device is not working correctly, or they are not reading the device correctly. But whatever mistake they are making it in all 4 measurements. So that's why their data is precise. Last measurement, These are the measurements, 4 measurements made by student C. The average comes out to 10.01, which is very similar to 10, which means it is an accurate measurement, and all 4 trials are giving you very close numbers as well, which means it's also precise. So that's the difference between precision and accuracy. Okay. Significant figures basically tell you how precise is your measurement. For example, if I want to measure, let's say, length of this object, okay, length of this line, I will use a ruler, and let's say I say it is around 10.6 inches. Somebody else comes in and they use their own ruler and they tell me it's actually 10.58 inches. So just because they added one extra digit, that means their measurement now is more precise. I thought it was 10.6, but actually it's not. It's not 10.6, it's 10.58. Somebody else can get even more precise measurement. For example, they can say it's not 10.58, it's 10.568, which means this is even more precise out of all these 3 measurements. So precision basically means how many digits do you see in your measurement. That tells you how precise your measurement is. More the number of digits, more precise your measurement is. So how do you get these sig figs? These are always indicated in measurements only. And for making a measurement, you need a device. For example, in this case, we are using a ruler. Or you can, if you want to measure mass of something, you would use a weighing scale. So basically, measurements are made by using a device. For example, in this case, let's say I want to measure the length of this particular box. And 2 rulers are given to me. If I use ruler number A, how will I give my measurement? This is the length of my object. So I would go right here. Okay. And I'll make my best guess. I know that the measurement is between 4 and 5, which means I know it is 4 something. It's not 4. It's not equal to 4. It is 4 something. So my best guess would be, I would say it's around 4 point, let's say, I'll say it's around 4.8. Okay, let's say these are centimeters. It's not given to us right here, but I'll assume the ruler is in centimeters. So it's 4.8 centimeters. I will now make the same measurement using ruler number B. Somebody would say in this top ruler, somebody might say it's not 4.8. What are you talking about? I think it's 4.7. Somebody might say, nope, I think it's 4.9. All 3 measurements here are correct. Okay, and I'll explain why in a little bit. Let's look at ruler B. I want to make a measurement with this now. So what I'll do is I will make a guess right here. Let's drag it down. Okay. So this ruler tells me this is 4 and this is 5, and I can also see these small marks right here, which means this is 4.5, 4.6, 4.7, 4.8, and this ruler tells me that it's 4.8, but it's not 4.8 because you can see this line right here is a little longer than 4.8. So again, I can make a guess and I'll say, oh, it's actually 4.82 centimeters based on this, which means this bottom ruler is more precise than the top ruler. Okay. Now the question is, why did I guess it's 4.8 from top or 4.82 from the bottom? Why can't I say it's 4.8222 centimeters? Why can't I do that? If you do this, this is wrong. Okay. Why? Because that is what is given by significant figures. How do you decide how many digits you can include in a measurement? There's always certain digits. Okay, certain digits includes all the numbers read directly off of the measuring device. So you will read what digits are given off of the device. For example, this device tells me 4.5, 4.6, 4.7, 4.8. I'm not making a guess here. The device tells me. So those are my certain digits. I will write down all my certain digits. And then plus 1 extra estimated digit. I can make a guess, but I can only make a guess for one of the digits. And that has to be my last digit. So I'll make a guess here. I'll say 4.82. Somebody can say 4.83. Somebody also can say 4.81. All of these values are correct. That last digit depends on how you are making your guess, how you are reading the device. So there is always a level of uncertainty in every measurement. And that uncertainty is given by the last digit that you see in your number. Okay, so remember, whenever you're taking any measurement using a ruler or any kind of measuring device, you always write all the certain digits first, which is given by that device, which should be marked on the device, and then follow this with only one guess or uncertain or estimated digit. That's your guess digit, that is an uncertain digit, or that is an estimated digit. Let's try that with an example. For instance, I have some liquid here in a beaker. We want to record the volume of that. We have transferred that liquid into a graduated cylinder, and we want to record the value of that as well. Important thing here, remember, for every measurement, it depends on the markings on the device. If your number would be 2 digits, 3 digits, 4 digits, that completely depends on how many markings you have on your measuring device. Every measurement should include certain digits, and these certain digits are the digits that are marked on the glassware. So if it tells me, the marking tells me this is 6, it is 6, and then plus 1 uncertain digit. You cannot add more than 1, and you cannot not add an uncertain digit. There should always be one uncertain digit. That could be any estimated digit or a guess digit that you make. So let's try with this. For example, this measuring device has these 3 markings, 40, 60, and something in the middle, which means this is 50. And I can clearly see that the liquid level here is less than 50. So I'm going to make sure that it is 40. So that's my certain digit, 40. And then it's greater than 40. So that is my guess digit. And I can only include one guess digit. So my number, this would be my final number. And you can make a guess. I would make a guess this is 48 ml. If you make a guess of 49, or you can say 47, it's all okay. Okay, but if you tell me it's 45, then you're clearly wrong, because 45 would lie somewhere in the middle of this, right? So you can't just pick any random number for the last number. It should still be based on the measurement or the value that you see there. Okay, now let's try the same with this graduated cylinder. So I see this big line is 40, this big line is 50. There are 10 more lines in between. So that means that's 10 ml divided in 10 lines, which means each line is 1 ml. So this is 40, 41, 42, 43, 44, 45, 46, 47. And you always read the lower part. Okay, this is how you read a graduated cylinder. If your liquid level is like this, you will always read the lowest part of the liquid. That is what we usually read through our eye. Okay, that is your number. So I need to read this number. Okay, and I know for sure my device is telling me what is this. This is 47. Right here it tells me it is 47. And it's slightly above 47. So I'm going to guess it as 47.1. You cannot stop at 47. 47 the device is telling me, followed by one more uncertain digit. You cannot forget the uncertain digit. If somebody says, no, I think it's completely matching with the line, there's nothing above this, which is also correct. You can say it's 47, but you do need to include one extra uncertain digit, and I think there's nothing else, so I'll put it as 0. So your 0 will be your placeholder in this case, if you think that is your measurement. Somebody might say 47.2, and that is also okay. But if you say it's 47.3 or 46.5, then that's completely incorrect, because you can see it from here. Okay, but if somebody says it's 47, then that is also incorrect. Why? Because then if you write 47, you're telling me 7 is your uncertain digit, which is not correct. Your uncertain digit, this device would always give you 3 digits, 47, and followed by something else, because I can see the mark of 47 on this. So 47 is not the uncertain digit. It can be 0, 1, 2, whatever you want, but it cannot be 47. Okay. One easy way to understand this is find your markings, the lowest marking on it. Whatever your lowest marking is, whatever the markings you see on it, and I would make my own marking in the middle. And that means these two numbers, whatever I see, followed by one more digit in the middle after that. Let's try with one more example. For example, we need to record this measurement. This is 100. This is 110, which means this is 105. And, oh, sorry, 100.5. Okay, oh, not 100.5. This is 105. Oops. 105. And I see 5 markings here, which means this is 100, 101, 102, 103, 104. So now this is 103. This for sure is 104. And my value lies somewhere right here in the middle of these two. Okay, my pen is not going very accurately, but you can make your own divisions in the middle here. Oops. You can make your own divisions in the middle here. This is, if I can mark it straight, this is somewhere right here. Oh, it's not the best. Oh, okay. My pen is not doing a great job at this, but you will be making a guess. You know it's not 103 for sure. Okay, let's clean it up. Oh my god. This right here, if I can draw it straight, is 103. This is 104. And the line that I see is right here, which is somewhere here in the middle. Like, not in the middle, but also somewhere in between 103 and 104. So what does this tell me? This tells me certainly it's 103. It is not 104. It is definitely 103, but it's not 103, it's 103 something. And that something is my extra digit. So I can't stop at 103. I will put one extra digit, which would make it, I'll say it's 103.3 or 103.4, whatever you want to guess. That is your final digit. Okay, this is my final guessed digit. There should always be one last digit, which is a guess digit. If I stop at 103, that is not correct. If I say it's 103.55, that is also not correct. Or let's say 103.45. That is also not correct. Why? Because this device can only give me one estimated digit. If I put a 5 here, then I'm guessing 2 digits, and I cannot guess 2 digits. I can only guess 1 digit. So remember, whatever the device gives you, you mark that measurement. So if this is, let's say 5, 6, I will mark this as 5, and then because my measurement is right here, I'll make one more extra digit, which is a guess. I'll say 5.5. If my device is like this, and now my value is right here. Let's say I'm making a measurement here. This is 5, this is 6. Then I know this is 5, 5.1, 5.2, 5.3. Then my certain digit is 5.3, and this one additional digit is going to be my guess digit, and I'll guess it as, I don't know, 2 or 3 or something. As long as you're guessing one extra digit, then that's okay. Now let's look at how do we count number of sig figs. Okay, there's only 4 rules. Let's just pull all of those rules up. There's only 4 rules for sig figs. It's not very difficult concept. How do you find the number of sig figs? The first rule is all non-zero digits are significant. That's it. If you see a number 1.00500600, let's say these are my values. All non-zero digits are significant, which means this is significant, this is significant, this is significant. Okay. All the interior, next three rules are all about zeros. Where you find the zeros, are these significant or not? So zeros can be found at three places, which means kind of like this. These zeros, they are in between two non-zero numbers. So these are called interior zeros right here. All zeros in the interior are always significant. So these two are significant. This zero is also interior between two non-zero. So that's also significant. Then all the leading zeros on the left are not significant, which means if I put a zero in front of this, all these zeros that are leading a number, meaning they're on the left side, they're leading it, they're leaders, they are not significant. Then the last place you'll find zeros are trailing zeros. Trailing zeros mean zeros on the right side of a number. So for example, like this, zeros on this right side. There are two rules for this. These trailing zeros are significant if a decimal is present in the measurement. These are not significant if a decimal is not present in the measurement. So in this case, I do have a decimal. That decimal can be anywhere in the number. As long as there's a decimal, these zeros on the right side are significant, which means however many significant digits you have, that's your number of sig figs. So 1, 2, 3, 4, 5, 6, 7, 8. So this value that I wrote here has 8 significant figures, or like I like to call them, sig figs. There are multiple examples here. For example, 1.5, yes, yes, 2 sig figs. 1 is significant, 5 is significant, 0 is interior, so significant. So 1, 2, 3, so 3 sig figs. If you look at this example, I know this is significant, this is significant. This is an interior 0, so yes. This 0 is on the right and there is a decimal in the number, so yes. All these zeros on the left side, not significant, never significant. There's no exception. So this is 4 sig figs. Let's try this number. Yes, yes. 0, yes, because it's interior. On the right side with a decimal, yes. So 4. If you look at this bottom number, 1, yes. 5, yes. 0 in the middle, yes. 0 on the right side, no. Why? Because there is no decimal present. So this has 3 significant figures. The next type of number is called a exact number. So far we saw measurements. Measurements means you are using a device. You're using a ruler, measuring device, measuring scale, or anything with gradations on it. Exact numbers are the numbers that are not measured. These are not measured numbers. These are exact numbers. Exact numbers have unlimited number of sig figs, or you can say this is ambiguous, meaning I cannot count how many significant figures are present in an exact number. These are the values for which there is no uncertainty. There is no uncertain digit in them. For example, how do you get exact numbers? There are 2 ways. The first way is you're counting numbers. For example, if I ask you how many coins or pennies do you see here, you'll say I see 1, 2, 3, 4, 5, 6, 7. You'll say there's 7 pennies. Nobody would say there's 6.5 or 6.8 or 7.2. Nobody would make those guesses. Why? Because you're obtaining this number by counting. So it's not a measurement, it's just a counted number. So there's these, how many sig figs are present here? I don't know. It's very ambiguous. Unless I tell you it's a measurement, you can assume it's an exact number. Next is defined value. Those also do not have any significant figures. For example, we might know that 1 kilogram is 1000 grams, or 1 kilometer is 1000 meters. This is a definition. Somebody defined 1 kilometer as 1000 meters, which means this is a defined value, so it does not have any significance. right here. So there's no significant figures or significant digits counted in it. For example, 3 feet is equal to 1 yard. This is a definition. Somebody defined 3 feet and said, okay, it's too many feet, I'm going to call it as 1 yard. Okay, so that is a definition, which means this is also ambiguous. This is a definition, so there's no uncertainty here. So no number of sig figs. You can try some questions. For example, here, how many sig figs? Yes, yes, nope, 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 because on the left. So 2 sig figs. If you do this, yes, 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 and yes, 4. Yes, 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 all non-zero, 4. Yes, it's a scientific notation. In case of scientific notation, we only look at the coefficient. This part is not significant. We don't care about it. This is the part that is significant. So 1, 2, 3. So that would be 3. This 1 dozen is 12. That is a definition, right? Which means it is exact number. So it is actually ambiguous. Or you can say cannot tell. It has infinite number of significant figures. This right here, nope, 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 because there's no decimal. Yes, so it has 1 significant figure, and that's it. Now let's look at the rules of significant figures when you're doing some type of calculations. There are 3 rules for it. When you're doing a calculation, you always have to carry your number of significant figures until you reach the final answer. For instance, the first rule is, if your question is about multiplication and division or if you only have multiplication or division in your question, the number of sig figs that are present in the result is the same number of sig figs as the measurement with the fewest number of sig figs. So if you're doing 2.8 multiplied by 1.444, then your final answer should only have 2 sig figs. How do I know this? I will look at number of sig figs in each of these values. This is 1, 2. This is 1, 2, 3, 4. This is 2 sig figs. This is 4 sig figs. The least of the 2 is 2. So my final answer is going to be same number of sig figs as my fewest number of sig figs in one of my measurements. And this rule applies for both multiplication and division. Let's try an example. For example, if this is your question, 5.02 times this times this. If you plug this into your calculator, it will give you this whole thing, 45.0118. Now, because this is multiplication, this is how many sig figs? 3. This is 5. And this is only 2 sig figs. Why? Because this 0 in the beginning is not significant. Out of the 3 measurements, 2 is the least number, so I have to reduce my number to 1, 2 sig figs, which is 45. And I'll explain why 45 and why not 46 or something in a little bit. Okay. You look at the number that's following this. So I want to stop right here. I look at the number that follows it. If this number is less than 5, you round the number down. Down means you forget whatever's written and you ignore it. Okay. If this number is greater than 5, you will round the number up. And I'll shortly explain what does that even mean. Okay. Let's try another example before that. For example, if this is my question, 5.892 divided by this, you plug it into calculator, it gives you all these digits. Okay. Now, because this is division, I count number of sig figs. This is 4 sig figs. This is 3 sig figs. My final answer is least, so it should be 3, which means this 0 is not significant. So I will not count this in. 1, 2, 3. My number should end at the 5, which means what is my following digit? It is a 9. I don't care what follows after 9, but I do care about 9. Because this digit is greater than 5, I have to round my number up. And what does that mean? I will simply add a 1 to this last digit. So instead of saying 0.965, it will become 0.966. That is called rounding your number. Okay, so rounding essentially means when rounding to the correct number of significant figures, you look at the number after the place of the last sig fig. So if I want 4, I'll count 1, 2, 3, 4, and I will look at the 5th digit on it, and only the 5th digit. We don't care about what follows after the 5th digit. If that number is anything between 0 to 4, you round the number down, which means drop all the digits after the last significant figure and leave the last significant figure alone. Okay. If you need it, you can add zeros to keep the value, which is, if you need 0 as a placeholder, you can write the 0, and I'll show you why. If your following digit is anything equal to 5 or greater than 5, anything above 5 or 5, then drop all the digits after the least sig fig and increase the last significant figure by 1. Add the insignificant zeros if needed in both the cases, which means you can add a 0 as a placeholder if that is needed in your case. That depends on question. Okay, for example, if we ask you to round this particular number to 2 sig figs, 2.34, currently it's 3 sig figs. I want to stop at 2, which means 1, 2. So I want to stop at 3. I look at the following digit, it's 4, which means I can just ignore it, round the number down, which becomes 2.3. Let's try another example. If I want to round this number down to 2 sig figs, which means 1, 2, I stop at 3, I look at the following digit, 7, which is greater than 5, so I have to round this number up. How? I will increase the previous number by a 1, so it becomes 2.4. It's kind of how you round your grades. If somebody gets an 89.8%, usually they'll quickly send an email to the instructor, hey, I would really appreciate if you could round this to a 90%. That's exactly what rounding is. Okay, so if it is greater than 5, yes. If it is less than 5, nope. Okay, let's try some more example. For example, this. If it's rounded to 2 sig figs, like the question tells you, round to 2 sig figs, so it stops 1, 2, following digit is 4. I do not care that the digit after 4 is 9. I only look at 4, which is less than 5, so I just ignore everything and it becomes 2.3. If you look at this number, again 1, 2. The following digit is 4. Now, because this is 4, it's less than 5, so I can ignore this number. But you can't just simply say and write, give me this as your answer. Why? Because this is wrong. Why? Because this number was 234. You cannot round it down to 23. Okay, for example, if I borrow $234 from you and I give you back $23 and I tell you, hey, I just rounded the number down to 23. That's not correct, right? If I borrow $234 from you, I can round it down to $230 and I give you $230 and I call it even. Okay, that's still okay, but rounding it down to 23 is not. That is when you have to use 0 as a placeholder. That is what the last point was in the previous slide. If your value, if you're getting rid of any of these digits before a decimal, there's no decimal. See in this number, if we look at this number, there was no decimal in this number. It is 234 and I have to get rid of 4 if I want to reduce it to 2 sig figs. Okay, if I keep the 4, it will always be 3 sig figs. I want 2 sig figs. So if I want to get rid of a 4, which is before a decimal, you cannot just get rid of it. You have to replace it with a 0, which is your placeholder. Now this is 2 sig figs. Why? Because there's no decimal here, so 0 on the right is not significant, whereas these two are. For example, let's try one more example. If I ask you, round this number to 2 sig figs. Okay, actually, yeah, 2 sig figs, which means 1, 2. Following digit is 9, so this would become 1.6 and you're done. Okay, if I say round this number down to 2 sig figs. Okay, or let's say I put a decimal right here. Round this number down to 2 sig figs. 2 sig fig means 1, 2, and my number needs to stop right here. The following digit is 9, which means this would become 6. I know that. But both of these digits are before this decimal. Okay? Either there's a decimal or there's no decimal in the number. But as long as these numbers you're getting rid of are before the decimal, you will be putting zeros as the placeholder. Which means if I borrow $1,594.6 from you, I should at least return $1,600 to you back. And not just $16. That would not be correct. That is called rounding. The next rule that we talked about sig figs is the second rule, which is addition and subtraction. If you're adding or subtracting any numbers, what do we do? How do we count sig figs till the final step? It is not counted by sig figs. When adding or subtracting measurements with significant figures, the result has same number of decimal places as the measurement with the fewest number of decimal places. So now we will not look at significant figures, we will look at how many place values are after the decimal. For example, if this is my number 5.74 plus this, plug it in the calculator, it gives you all of this. Now we need to get the final answer with the right number of significant figures. The rule is least decimal places. So how many values do you see here after decimal? 2 decimal places. How many digits after decimal? That's basically it. This is 1, 2, 3. So 3 decimal places. Even a 0 after that would be counted. Okay, so 1, 2, 3, 3 decimal places. The least is 2. So my final answer should stop at 2 values after decimal. The following digit is 4, less than 5, so I just get rid of it. It becomes 9.21. Remember, multiplication or division. In this case, we look at least number of sig figs. But when you're doing addition or subtraction, you look at least number of decimal places. Those are the rules that you should remember. Okay. Another example, 4.8 minus 3.965. If you plug this into calculator, it gives you this. But this is 1 decimal place. 1, 2, 3 decimal place, least is 1, so my final answer should stop right here. The following digit is 3. I don't care there's a 5 afterwards, but it's less than 5. 3 is less than 5, so it is 0.8. And this 0 is not significant. Why? Because it is 0 leading 0. 0 on the left side. They are never significant. Okay, so those are the 2 rules. Now the last rule is the third rule. The third rule is, if in your calculation all multiplication, division or addition, subtraction, everything's basically present, which rule will we apply? The rule is, if calculation involves multiple steps, wait until the end to round to the correct number of sig figs. You cannot round it. Let's try an example. For example, this 3.489 times this. If it's multiple things, this is multiplication, this is subtraction. I know all of them have different rules. So what do? We follow PEMDAS. This is basically from math. P means parentheses, E means exponential, M means multiplication, D means division, A means addition, S means subtraction. So PEMDAS is basically the flow in which you are going, the order in which you are going to solve this question. So you always start with parentheses and you end with subtraction. So I do see parentheses here, which means I'll first solve for parentheses. So I'll do 5.67 minus 2.3. My calculator will give me a number. Okay, 3.37. But I will not round it yet. I will make a note. Because this is subtraction, the rule is decimal place. This has 2 decimal place. This has 1 decimal place. So my final answer should have 1 decimal place from here. But this is not my final answer because I still need to multiply by this. So I'm not going to round the number yet. I will just make a mark for myself after 1 decimal place. So now when I do count the number of sig figs from here, I should count it up until the mark that I made. So let's do the next step, which is this multiplied by that. If you plug this into your calculator will give you a number. Let me plug this into the calculator real quick. It's not on the slides. So if I do 3.37 times 3.489, my calculator gives me 11.75793. That's what my calculator gives me. Now I look at, because this is multiplication, the rule is based on sig figs. This is 1, 2, 3, 4, so 4 sig figs. This is 1, 2. Why 2? I do not count 7. Why? Because I made a mark for myself. When I solved the parentheses, it told me 1 decimal place, so I made a mark at 1 decimal place. So this is only 2 sig figs. So out of 4 and 2 sig figs, 2 sig figs win. So my final answer should be 2 sig figs, so it would end right here. The following digit is 7, which is greater than 5, so I will round the number up and it becomes 12. So the idea here is, whenever you are solving with multiple steps, you do not round your digit until you reach the final answer. What does that mean? For example, this was 3.37. I know it should be 1 decimal place. I'm not going to round this to 3.4. That would be incorrect. It would give me the wrong answer. So you should keep a note. Don't forget it. Don't ignore it. You still keep it 1 decimal place. You keep a note of it, but you do not round until you reach your final answer. And that was the third rule. So addition. First rule is multiplication. Oops. Oh no. I erased it all. The first rule is multiplication or division. You look at least sig figs. When you're doing addition subtraction, you look at least decimal places. When you have a combination of both, then you only round the final answer. And you make note for yourself like this by drawing a line in between. And that's it. Those are all the rules about significant figures and how to do calculations with them.